Okay, we have a few more problems that we're going to go through. Let's look at problem 44. Here we have a function f of x, which is equal to x squared over x squared minus 9. X squared minus 9. Like before, we want to first, before we even start with taking the derivative, because remember we are looking for whether or not this is increasing or decreasing, or where it's increasing or decreasing. And our first step there is to take the derivative. But before we do that, I do want to look at what the domain of this function is. What are the possible problem spots in this formula? Well, of course, we have a fraction. So in a fraction, we are going to think about where the bottom equals 0. Where does x squared equal 9, essentially? Of course, that's when x is going to be either 3 or negative 3. I'm just going to go ahead and write that as the domain is all x's, where x is not plus or minus 3. So we have to leave out plus and minus 3. Now we take the derivative. Of course, this is a quotient, so we're going to use the quotient rule. Remember how that quotient rule goes. We take the derivative of the top. Derivative of x squared is 2x. We multiply that by the bottom, this x squared minus 9. Then we subtract. We take the top as it is, times the derivative of the bottom. The derivative of x squared minus 9 is a 2x. The 9 just goes away. Of course, then we get to divide by what was originally on the bottom, the x squared minus 9, but squared. And I would like to go ahead and simplify this. For one thing, we have a 2x cubed, and here we also have a 2x cubed. Those actually will cancel each other out. What's going to be left is the 2x times the negative 9. That will simplify down on top to a negative 18x. The bottom stays x squared minus 9 squared. So all the other two terms that we would have had on top, they cancel each other out. Next, we need to find out what our critical points are. Remember, we have two questions here. We're asking, where does this derivative equal 0, and where does this derivative not exist? Well, when we have a fraction here, setting it equal to 0 is really just setting the top equal to 0. So we're asking, where is negative 18x equal to 0? Of course, that's only when x equals 0. If we look at where this doesn't exist, we're basically asking, because we have a fraction here, where is the bottom equal to 0? When is x squared minus 9 quantity squared equals 0? Well, of course, that really is just when x squared minus 9 equals 0, or when x squared equals 9, when x is equal to plus or minus 3. But note here that technically these are not critical points. These plus and minus 3 are not in our domain. Those are completely outside our domain. A critical point for a function has to be in the domain of the function. So the only critical points here, well, there's one critical point here, x equals 0. This is our critical point. The x equals plus or minus 3, we don't want to ignore them. We actually do care about them. These will be in our number line, but not because they're critical points, but because these are discontinuities. We need to include those. So if we make a number line, we're going to include negative 3 and 3, and we're also going to include 0. Those are all important points. Of course, we still have our derivative, our formula for the derivative, and we're going to take test points in all four of these intervals, from negative infinity to negative 3, from negative 3 to 0, from 0 to 3, and from 3 to infinity. From negative infinity to negative 3, just pick the number closest to 0, that's an integer, because that's going to be the easiest one to plug in. going to go ahead and plug in negative 4. Plugging negative 4 into this equation, we have negative 18 times negative 4. It's actually equal to 72. Then we have negative 4 squared minus 9. That's 16 minus 9. Just 7 squared is 49. But the important thing here is that this is a positive number. In fact, we can kind of ignore the bottom because the bottom is always going to be a positive number. But I'm going to go ahead and write it out anyways. For negative 3 to 0, I'm going to go ahead and pick negative 1. Again, pick whatever number you feel the most comfortable with. I always like to pick the smallest numbers that I can that are not fractions. And then pick the fractions with the smallest denominators that I can, if I have to use a fraction. Of course, when I plug in negative 1, again, the bottom, technically we could kind of ignore it, but it will become 1 minus 9, or 8 squared, or negative 8 squared, which is a 64. On top, that's what's actually going to determine the sign. We have negative 18 times negative 1, which is a positive 18. And so overall, this fraction is positive. So this was positive and positive. If we move on from 0 to 3, again, just going to pick 1. This time, it actually doesn't change the bottom because the square here got rid of the negative anyways. So we still have a 64 on bottom. On top now, we have negative 18 times 1, which is a negative 18. We have a negative value this time. We have a negative there. And then finally, from 3 to infinity, essentially the negative 4 here, I'm going to pick a positive 4. Things are nice and symmetrical here. Again, the bottom is going to be the same as the 49 that we had the first time, and the top, because we don't have the negative on the 4 anymore, is going to be a negative 72. So we get a negative number. So here we know that our function is increasing from negative infinity to negative 3. It's increasing from negative 3 to 0. It's decreasing from 0 to 3. And it's decreasing from 3 to infinity. I'm just going to go ahead and write those all out. Now, in our last example, we actually had a case where we had two increasing intervals right next to each other. And we saw from graphing that we could combine those two intervals together. However, in this case, we can't do that. And it's a little hard to see why if we don't graph it first. So our function f of x was equal to x squared divided by x squared minus 9. We have this graph right here. So first of all, let's go ahead and plot our critical point. Remember, we had 0, 0 as a critical point. Technically, x equals 0 was what we knew, but 0 is the y value of that. We also had discontinuities at negative 3 and 3. Those do not have points on this graph. In fact, we have x equals 3 and x equals negative 3 are actually asymptotes for this function. And now we can actually think about what's going on in this. From negative infinity to negative 3, as our x values go through there, it is an increasing function. It increases slowly over here, but it is increasing the entire way. At negative 3, however, it suddenly jumps down to minus infinity. And it increases from minus infinity up to 0 as x goes from negative 3 to 0. So it is increasing on this interval here, but if we took both those two intervals together, it definitely is not increasing the whole way. It made this big jump in the middle of it. So points over here are definitely higher than points over here, despite these x values being lower than the x values over here. So we this time we cannot combine those two intervals. Same thing on this side. We have it's decreasing as x goes from 0 to 3. It decreases from 0 down to minus infinity. and then suddenly jumps up and decreases from infinity to, well, probably about 1 as x goes from 3 to infinity. So definitely increasing here, decreasing here, and decreasing here. Now let's look at problem 46. Problem 46 is a little bit different from the ones we've been doing. We solve a function f of x, but this is going to be a piecewise function. We're going to have two parts to it. When x is less than or equal to 1, it's going to follow the formula of 3x plus 1. When x is bigger than 1, it's going to follow the formula of 5 minus x squared. In this case, again, our domain is going to be everything. We actually don't have a problem with domain in this one. We have a definition for what this function gives for any point in the real line. It's just that we have two different definitions depending on whether or not we're above 1 or below 1, or below or equal to 1. The domain does include 1. We have a definition there. But we don't have any problems with these formulas on the regions that we're using them. When we differentiate a piecewise function, we are able to differentiate each piece separately. So this 3x plus 1, we can differentiate that and get a 3. The 5 minus x squared, we can differentiate that part. The 5 goes away, and the x squared becomes a 2x. We have a minus 2x. The one thing we need to be careful about, though, is that these formulas will only work on the inside of these intervals. So the interval here, we could say, is 1 to infinity. So we can still use that same 1 to infinity for the negative 2x. We're not including the endpoints anyways. So negative 2x is still going to work for x is bigger than 1. When it comes to the 3x plus 1, originally that was true for the interval negative infinity to 1, including the 1. For its derivative, we cannot include that 1 anymore. We can only say this is true for x is strictly less than 1. Those endpoints of our pieces are potential problem spots. And we might have, it might still be differentiable there, but it's not for sure. We have to treat those separately. Now in particular here, the derivative will exist at 1 if both the function itself is continuous there and the formulas for our derivatives also match up. So we might have to check that. In fact, let's go ahead and check whether or not the derivative exists at 1, because it's going to be relevant to talking about increasing or decreasing. So first, let's check if f is continuous. To do that, well, first of all, we notice that f of 1, we just follow this first formula, we're going to get 4. To find the limit, though, we're going to have to take one-sided limits. We're going to have to take the limit from the bottom. That's going to follow the formula 3x plus 1. And we're going to have to take the limit from the top. That's going to have to follow the formula 5 minus x squared. So what is the limit of 3x plus 1 as x goes to 1 from the bottom? Well, because this is just a polynomial, this is actually a linear function, we can evaluate it by just plugging in x. X equals 1. Which, of course, is the 4 like we saw before. It's what happens on the other side that's a little bit more important, though. Here, again, it is a polynomial, so it is actually easy to evaluate the limit. We can find it by just plugging in the x equals 1. And the fact that we did get a 4 here, 5 minus 1 equals 4, means that the function itself is actually continuous. The limit of this function at 1 is 4, which is the value of the function. Okay, so the function is continuous. Is it differentiable? does the derivative exist? We're going to have to do the exact same thing, but now we're going to find the limits of f prime. Let's see. F is, how do I write this? F is differentiable. Here we're going to take the limit of our derivative as x goes to 1 from both sides. Well, when x is going to 1 from the bottom, we're going to follow the formula for x is less than 1. We're going to put in a 3. And of course, well, should probably put my limits there still. The limit as x goes to 1 from the bottom of 3. Of course, that limit, because we're dealing with a constant, is just going to be a 3. If we're coming from the top, our derivative there is negative 2x. So we're taking the limit of negative 2x as x goes to 1 from the top. Of course, that just means because we're dealing with a linear thing here, we just get to plug in 1. Negative 2 times 1 gives a negative 2. These are not equal. So f prime of 1 does not exist. That's important. And that's not obvious unless we actually take these limits. Now, we could have probably skipped the f continuous part, but it is actually possible for the one-side limits for the derivative to be the same and not actually be continuous. Maybe the function is going up, but then it jumps up and continues going at the same slope, but then the derivative still wouldn't exist at that point. So really, we have to check both of these. We should really always check, if we're dealing with a piecewise function, whether or not it's continuous and whether or not the derivatives match up at that point, or those points if there's actually more than two pieces. So when we're trying to find our critical points, 1 is in the domain of our function, but the derivative does not exist at 1. So 1, x equals 1, is a critical point of our function. Now, that doesn't mean it's the only one. We could also go ahead and see where the derivative is equal to 0. Basically, where would our pieces potentially equal 0? Now, since our derivative actually has two pieces, we'll go ahead and try both of our pieces. For our first piece, the derivative is equal to 3. Is 3 ever equal to 0? For any x value? No, that's not true. So there's no solutions over here. On the other hand, we have the piece where our derivative equals negative 2x. Is negative 2x equal to 0 ever? Well, if x equals 0, so it looks like maybe we have another critical point at x equals 0. The problem here is, when x equals 0, we're following the 3x plus 1 piece, because 0 is less than or equal to 1. We're not following the 5 minus x squared, so we're not using the derivative of negative 2x there. So you could say that x equals 0 is a critical point of 5 minus x squared, but it's not a critical point of f, because f is not following that formula when x equals 0. So in fact, x equals 1 is our only critical point for this function. That's our number line. Very simple number line. We can go ahead and take test points. We're going to take a point in the interval from negative infinity to 1. Might as well go ahead and pick 0. But it really doesn't matter, because anywhere below 1, we're following the formula of the derivative equals 3, which is obviously a positive value. For the 1 to infinity interval. I'll go ahead and pick 2. Remember, our formula there is -2 times x. So -2 times 2, sorry, it should be a -4, which is obviously a negative value. So it's going to be increasing from -infinity to 1, and it's going to be decreasing from 1 to infinity. And we can go ahead and actually graph this function. Now, actually graphing this function in GeoGebra is a little tricky. We have to use that if function. So we're going to say if x is less than or equal to 1, we follow the formula of 3x plus 1. If not, we are following the formula 5 minus x squared. And we get this graph right here. It is definitely following 3x plus 1 until we get to x equals 1, which is the point 1,4. That's our point up here. So we're following the formula for that line, and then we follow the formula for this quadratic. It is definitely a nice enough function, though it does come to kind of a point here. The fact that this is a sharp corner is why our derivative doesn't exist there. It is a continuous function there. There was no real break in our graph, but it was a sharp corner. There's no tangent line here. But we can also see that on this side, we definitely were increasing. In fact, increasing with a slope of 3 at all times. On this side, we are definitely decreasing. We are always decreasing. If we were to actually graph the entire 5 minus x squared, you can see where that other critical point was that we found, the x equals 0, but it's not actually part of the function f that we had originally. We don't care about this critical point because the critical point for if we actually extended this piece to everything, but it's not actually a part of the function f. So all these kind of things that you would have to think about in these more complicated looking functions. Though we don't really run into these kind of functions very often. Most of the time we just have a formula and we can just go ahead and just follow this process every time. Alright, so quite a few examples here. Hopefully going through all these examples gave you a good idea of what to expect with these kind of problems. We're going to be using these ideas of critical points, increase and decrease, all that kind of stuff quite a bit going forward. In fact, these critical points are going to be incredibly relevant coming up in the next section. And so so make sure you get used to these kind of things. And I'll see you guys in that next video, in that next section.